Ciao friends! With the new composite models over analysis services, DAX has been enriched with several statements, define columns, define tables, and several functions. Now, among the many, I was curious to check the define column statement. Define column works like magic. You can create temporary calculated columns inside a query. I wanted to dig a bit deeper. I wanted to understand the query plan, how the DAX engine solves the problem, what is the query plan that is generated when you use define columns. That's why in this video I'm going to write some simple code in DAX, look at the query plan and understand how DAX generates the code that solves the define column statement. I will also try to write the same code with define columns and without it, just by using regular variables, to check the complexity of the two scenarios, to check how easier the code is when using define columns, and this will naturally lead to a bit of analysis about the performance of using define columns or avoiding it. To be fair, I do not expect define column to be faster or better than regular DAX code, just because define column has been introduced right now, so there is a lot of time to make it faster and make it better. To me, honestly, it is just incredible that it works, because it's a beautifully crafted piece of engineering that greatly enriches the DAX code. But that's enough for an introduction. Let's go straight and start writing some DAX code together. I have here my usual Contoso model. It contains sales, customer, store data, and product and promotion. And I'm going to write queries. I need to write a query because define columns requires me to have a query. It would not work inside a measure. So because I will want to create the same query with define columns and without define columns, I start by preparing two windows, one containing where I enable query plan, I enable server timings, and here I will write the code with define columns, and in a similar window with query plan, server timings enabled, I will just write the same code without the define columns to check the two side by side. Button layout here too. Okay. Let's start with something simple. I start just by creating one calculated column in customer containing the sales amount, and then I sum it. I'm actually cheating a bit, because if I create a calculated column that contains the sales amount and then I group it by some other column, I do not expect DAX to perform really well on that. But I want to understand how the code is being generated. So let's start with the define column customer sales, which is just sales amount. And then I summarize, we summarize by continent, for example, by customer continent. And we create a column amount, which is, no, not sum, but sum of customer sales. So I create a column and then I sum it later. As I said, I'm kind of cheating because I expect it to generate a table containing the sales amount for every customer and then sum this again, which is suboptimal because it could actually group by continent, but maybe they already optimized it in such a way that it works. Let's check that we have some result, and we do. The query plan is actually very simple, just a few lines of query plan. But if we look at the server timings, let's zoom in a bit. Of course, it's super fast, but there is a first query which computes my sales amount measure by customer key. So that is computing the sales amount for every customer. And this is the column definition, retrieves 18,000 rows. That is one row per customer. And then we have another query that uses a callback data ID to compute some X over quantity by net price by customer continent. So this is actually computing by customer continent the sum of this expression, which is a callback data ID of sales amount. So it's actually not aggregating the values that are computed here. It's actually computing the values again, because in this query, it just retrieves it. No, I'm wrong. It's using this callback data ID, but it's computing the sum of the expression from customer. So this is not grouping by sales. It's grouping by customer continent and computing again the callback data ID. It looks like it's computing the same value twice, which is kind of strange. But I mean, that is what it is. What if we write it without the find column? Let me get rid of this. We can just write an evaluate summarize columns by customer continent amount, which is just our sales amount. And if I run that, it doesn't work. No, it worked. We do have, looks like it's not working. Okay, let me close that and open a new one. We re-enable server timings, then query plan. We put that in bottom layout, run it. Okay, now it works. The query plan is very simple, and let's look at the server timings. I would expect this to be better. Indeed it is. You see that we have the expression of sales amount and then the grouping by customer continent, the sum of expression from sales. This time it's not from customer, with a join over customer. So this has been entirely executed by the storage engine without ever querying the formula engine. Whereas in this query, we have this callback data ID, and we know callback data ID are quite never a good thing. I want to do another test. What if I summarize columns and I do for each? I'm mimicking the same expression that I would expect it to do. I do a sum x over customer of sales amount, because if we look at how we did this, I created the customer sales column in customer, and then I'm summing the column from customer, which is kind of what I'm doing here. For each continent, I'm iterating over the customers in the given continent, and I'm computing sales amount customer by customer. So I would expect this query plan to be similar to the one created by the query column. Let me run it. It's a bit slower, and it is indeed very, very close. We have this first query that computes by customer key the sum of expression, which is my sales amount. And then we have the same code. Yeah, basically what we are doing by creating a calculated column, we compute the code this way, but it's actually like if we did it this way, by having an iteration over the customer and then computing sales amount. So the code is not really optimal. The engine could have figured out that this sum is again over another measure that is additive. It can be optimized, and the benefit that we obtain is not really that large. What if we do something a bit more complex? For example, let's say that I want to count all the customers that bought more than the average. So I will want to compute the average sales of all the customers, and then count the number of customers that bought more than the average. In this case, I will need to have the sales customer by customer, so I will need to have the double iterations, and maybe here calculated query columns are going to be better. So we are in query 1, and we define the column. We summarize again by continent. I want the number of customers This is just a count rows of customer. And then the number of customers that bought more than the average, more than average. To do that, more than average, I need a variable. Let's call it average sales. And this is nice because I can use average X over customer of customer sales, which is a column, so customer sales. And then I do a count rows of customer, of filter customers, where customer sales is greater or equal than average sales. Close that. And that's it. Now you see, now using columns is quite kind of nice to read, because this average X is iterating over customers, and this is computing the sales amount, and that is not bad. It's probably a good example for calculated column, for query columns. We have again our query, the first query that computes the sales amount customer by customer, from sales left outer join customer. Okay, this is computing 18,000 rows, which are the customer. And then we have again our callback data ID. So SMX over sales amount. This looks like the calculated column, the query column, recomputed, select customer continent, count, and sum to avoid blanks. And now we have the second column being computed. So select customer continent from customer, and we have this callback data ID that computes customer sales, which is actually sales amount, etc., where the value is greater than the callback data ID of average sales. That is not really a beautiful query plan. It's very fast, 45 milliseconds, but it's not really beautiful. What if we write everything with just variables? It's probably easier if we start from here. If we didn't have defined column, we would need to compute an average X over customer of sales amount. Actually, it would be better if we create a table containing the customers with the sales amount, and then we average X over that. So let's call this table customers and sales, where I use add columns over customer. And I create a new column, customer sales, which is sales amount. Then average sales in average is an average X over this variable. And we use customer sales. And here, there's no point in filtering customers. I would filter customers and sales, where the variable that we computed earlier is greater than the average sales. Okay, without the defined column, I would write the code this way. If I did it correctly and I run it, it's again a bit faster. 31 milliseconds against 45 milliseconds, but what really makes the code better is that we don't have any callback data ID here. You see that we have the count of customer continent. This is computing only our count rows. Then for 18,000 rows, that is the customers. We retrieve by customer the sales amount. And this is retrieving customer continent and customer key. So what looks like is that the engine is retrieving the relationship between customer key and customer continent. It's retrieving the values of the sales amount by customer, so the result of this table, and everything else is happening in the formula engine, which is kind of large here. And it's much smaller here, actually, even though we need to take into account that we have callback data ID, so this value is not really important. Anyway, also in this case, you have seen that you can author the code using defined columns. You can also author the code using regular variables. And it looks like the code with regular variables is still a bit better. When you define a column, it actually materializes this column, so it generates the column that you have created. But what looks strange, at least to me, is that it seems like it is computing the same value that has been materialized here. So it materializes the value, but then it computes it again. Even if this is maybe it's just the syntax of XMSQL and it's retrieving the value from the table that it created. Anyway, it's kind of fast. Now, what if we go a bit further? So we try to do something more complex. I'm a big fan of ABC analysis because it's a very good example where the ABC analysis created with calculated columns is likely to be much easier to read. With variables, it will be much more complex to write. But let's give that a try. So query 1. If we were to build ABC analysis just with columns, we would need one column with the sales amount. So define column customer. Yeah. ABC, no, not on customers. We do that on product. Product sales, which is just the sales amount. Then we need the second column, which is product sales running total. Product sales running total requires a SMX over a filter of product. This is kind of neat. I can use the product sales column immediately. Where product sales is greater or equal, I need to save the current amount. Current amount equal product sales. Because I want all the products whose sales is greater or equal than the current one. And out of this, I compute product sales. Let me see if we are computing something good. Evaluate. Summarize columns by product name. Now let's use a select columns. No. Actually, I can make it even easier. I can just evaluate product. The column should be there. Define column, define column. Oh, this define is not needed. Yep, if I look at the result, I have all the columns in product, and I also have product sales and product sales running total. If we use order by product sales descending, I have for the first product the product sales, then the running total that grows and continues growing. So that's good. Then we need the third column. Let's format the code. Let's format the code this way. The third column is to transform the product sales running total as a percentage. So sales running total as a percentage. That requires me to divide the running total, so this part, by the sum of product sales, so the grand total of product sales. I have my third column, I run it and it doesn't work. Yes, I didn't close divide. Result, and I have my percentage, which is cool. Finally, I need to compute the ABC column product ABC class. This is just an if that says that if this is less or equal 0.7, then it's class A. Otherwise, if this is less or equal than 0.9 is in class B, otherwise is in class C. And if I run it now, I have, for each product, it's ABC class. That's exactly what I wanted. Now, I don't want that. I want to do a summarize columns by product ABC class. And I want the number of products, which is count rows of product. And I want the amount, which is sales amount. Okay, so this is the entire code, which is really nice. That I have to say, this query is simple to read, is simple to understand, and it's just beautiful. Regarding performance, I have no idea what to expect. It's not that bad. The query plan is very simple. The server timings, I don't have any server timing. Why that? Let me try that again. Okay, now I have it. Well, 3.2 seconds, not really super fast, and we have again a lot of callback data ID with a lot of select columns. So we could go further in analyzing, but for the ABC analysis, it's not going to be beautiful. Anyway, 3.2 seconds doesn't look really bad. But what if we do that with variables? With variables, it's harder. We need to think more, because if we want to compute everything with variables, we need to start by define. No, we can just go with evaluate. We first need products and sales, where we do an add columns to product A to product. And we compute amount, which is sales amount. Return, as we did earlier, let's check that we are actually computing something good. Okay, this is returning the products, and for each product I have the amount. Then I need to add the running total, and because I have it in a variable, I need to use another column, another add columns, products and sales running total. That's an add column to product and sales. And we create amount running total. As we did earlier, we save in a variable the current value of amount. Current amount is just the value of amount. And then we iterate over product and sales. No, not over product and sales, over filter product and sales, where the amount is greater or equal to the current amount. And out of this, we compute the amount. This should close at columns. Okay, let's return products and sales running total. Order by amount, descending. Okay, so we have the value and then the running total that grows, grows, and grows. Finally, we need to transform that into a percentage, meaning another column, products and running total percentage. I have no idea whether I can use a percentage symbol here. That's another columns to products and sales running total. And we create amount running total percentage, which is divide amount running total. I need the grand total sales, which is a sum x over, I can use the first variable of the amount, and then I can use total sales here. Okay. It turns out I cannot use a percentage. Let's use PCT. Now, results, and I have my amount running total as a percentage. Finally, I computed the ABC class. Var products and ABC, add the columns to this table, ABC class. Let me copy the code from here because it's actually the same. Here we close at columns. The only thing that changes is the column name, which need to be this one. Okay. Now, if I return products and ABC, it doesn't work. Oh, because yes, I cannot use the product table. No results. Now I have for each product the ABC, which is exactly what I wanted. But you see, here is where you really appreciate the calculated columns, because I can do a summarized column by product ABC class. It's very easy. Here I cannot group by products and ABC in a simpler way, because I could use group by. Actually, yes, I could use group by. I can do a group by products and ABC. I group it by ABC class. I want the number of products, which is account X over current group. Well, I prefer to write it as sum X over current group of 1. And then what I wanted is also the amount. You see, here it's very easy. You just do sales amount. Whereas with group by, we need to write some more code. Amount It's a sum x over current group of the column that contains the amount, which is amount. It does not work. Why? The column amount does not. Oh, no. Oh, yes, that's not a string. That's a column. Not yet. Let's get rid of the order by. Okay. We have our result 380, well, 2.663. Let's check if it's right. 2.63. So the numbers are the same. The query plan here was 3.2 seconds. Here, the query plan, well, it's actually kind of way better, 400 milliseconds. Everything is being executed in storage, in Formula Engine. You see that the part of storage engine is really tiny. Here, the entire code is executed in Formula Engine. Here, it's harder to tell because actually there are a lot of callback data ID. So this value for storage engine, I'm totally not sure that it is really storage engine. Here, it's very clear that we are using Formula Engine a lot, but it's way faster, 400 milliseconds against 3.2 seconds. Code here is very simple because actually the only thing that the storage engine retrieves is this query that retrieves quantity times net price for each product. Everything else, so the entire piece of code is executed in Formula Engine, which is not really good. But again, if you look at this code, we wrote it step by step and it's kind of long. And also hard to understand. It's not very easy. Whereas if you look at the same code written with defined columns, it is way better. So it's much easier to read, even though I have to say it's also slower, which is kind of totally expected. I was not expecting this code to be faster than the version with variables. So at the end of this quite long video, I guess, you have seen that we can write code using defined columns. Performance is not the best. It can be better. But with that said, I didn't expect performance to be better, and I also understand that it is totally unfair to do a comparison with a product that is currently in test, so it's not final, and it came out a few weeks ago. So I think it's totally wise that at Microsoft they are focusing on making it work before optimizing it. Optimization will probably come later. So we are comparing an engine and techniques that have been optimized for years with a new feature that has only a few days of age. So it's totally unfair to do the comparison. But what I wanted to understand is just the kind of queries that are executed. And it looks to me that the engine actually materializes the calculated column, even though it is kind of strange that it looks like, at least by looking at the XM SQL code, that the same code is executed multiple times. So I will need to investigate more about that in order to understand exactly what happens under the hood and have a better picture of how calculated columns in queries are working. Enjoy DAX.